It's my pleasure to be here, and my first slide is to show you that it's a different, give you an impression it's a different talk. Before they start that, I want to say really clearly that I believe AI is a tremendously powerful and good tool. The first two speakers have given you some idea of that. I actually think AlphaFold is such a tremendous advance that they should get a prize. There's the two lead authors. They should get a prize. I don't see how the Nobel Committee would ever give them one, even though they deserve it because of what they've done for mankind. Okay, so here I'm going to talk about AI for the universe, which is shorthand. So one of my students many years ago, during our meeting, we'd always put up a to-do list for each person, and his number 3 was software for the galaxy. And all the other students were impressed. And it was because he had the right software about what signal we should expect from the galaxy, but it wasn't for the whole galaxy. The fact that we're using AI to explore the universe, and I'll give you some examples, but that picture gives you an idea. That's an AI picture. This is an AI-generated picture. It's not the one from Hubble, it's the actual AI-generated picture. So, AI for the universe. So, AI has been proposed or been used to help us do things like look for signatures of life on Mars, and I'll mention that briefly. Understand why the sun's corona is hot as it is. It's hotter than people originally expected. Why stars have certain ages and what they're doing and what that might have to do with the evolution of the universe. Things like how galaxies form, and I'll show you some examples of classification of galaxies. And astronomers and astrophysicists and many other people are using neural networks to dig deeper in the universe than ever before. And there are reasons why that has to happen. I'll give some examples. And this is happening at a time when the research groups are getting bigger and more complicated because the problems we're dealing with in astronomy and astrophysics, or the gravity detectors, those are very large collaborations. And they're running very big organizations, same way in hydrogen physics and so forth. So we're already facing a point where the accountability and the knowledge in the group is diffuse, and now you're bringing AI in, and particularly neural nets, because those tools were made available roughly 5-6 years ago, and almost nobody understands deeply how neural nets work. So that's a problem. How do you validate that what's going on? So we're going to make great discoveries. Some of those are going to be wrong. I mean, really wrong. Some are going to be embarrassingly wrong, and some are not going to be quite so embarrassingly wrong, but still be wrong. So that's one of the things I'm concerned about, and you'll hear how I drift off in my talk towards the end, explaining why it's an issue and what we have to think about doing. AI already interrupts our lives. So if you've ever, heard about a great new restaurant that just opened up, and you go and try and get a reservation, you can't. Why? Because bots, AI systems have gone in and got all the reservations, and they're selling to them. I wanted to go to get a concert ticket. As soon as the tickets went on sale, they were gone. We had to pay extra money to buy tickets from somebody who bought the tickets and do it. So AI is already impacting your life in ways you don't even pay attention to in some sense. Fortunately, after the Taylor Swift debacle, they actually clamped down to make sure people aren't charging too much extra. AI is in your face. AI is in your life. We're already starting what's going to be a tremendous decade increase in everybody having AI doing stuff to them all the time. So here's an example of one of the things that makes me a little bit concerned about AI, but on the other hand, I really find it interesting. So I don't know if you remember, but a couple of years ago, there was the collaboration that tried to make a direct image of a black hole. And the image on the left there is the image that they made from using basically telescopes around the world and synthesizing the image. And they got this image where the black hole's in the center, and there's an accretion disk, and the accretion disk is not uniformly illuminated because as the stuff is spiraling in, the light also gets spiraled around on the way out. And so they have created an AI program which actually tries to do it. So you see in the middle picture what the AI program predicted that this data should be showing. But this AI program is based on assuming general relativity is correct and a very strong field limit, and doing the calculations, assuming how stable the disk is coming in, doing the calculations, both of the particle orbits coming in and the photon orbits coming out, and then they blur it to what it's with, and they said, all right, we've made an image which is twice the resolution of the original just straight reconstructed image by using AI. And I'm not surprised, it kind of looks like what I expect if general relativity is correct. It's trained on a data set which is done by a huge number of high fidelity simulations using general relativity. And we'll come back to this kind of an issue, but this is an issue but you're going to do it because maybe you'll see something, maybe you won't, right? But somebody's going to get their thesis out of this, right? So here's a problem that you understand the AI had to be used. So you're going to go to Mars, which is a relatively nearby place, but if you're going to go explore the universe, you're going to send these rovers to Mars. You can't drive them the way you drive the car around your kid drives the car around on the carpet, because when they go too fast, they flip over, they bump into something, they flip over. You can't have that happen. And the round trip time to Mars is more than a half hour. It's typically an hour for the light. You can't control it remotely. So it's got to drive itself. It's got to look at the environment and say, is it dangerous if I roll the wheel over this thing? Is it going to flip me over and so forth? And so all three recent rovers all have AI driving, pretty much like the AI cars that drive around San Francisco, which actually do better than people, but aren't perfect, right? That's what's going on. But another application is Mars is far enough away, the power, for the transmitter up to the satellite going around Mars and then back to the Earth, it's limited in bandwidth. You can't send back all the pictures it takes, all the images it takes. So there's AI choosing which pictures to send back. So they're sending back things that the AI think is interesting. What if there was something really amazing, like a tomahawk or something, some primitive tool, and you don't send that picture back, right? Okay. But they also, as I mentioned in the first slide, there is software that's designed to look for carbon, and it has been trained on carbon samples on the Earth, and it gets 90% of the time it gets right in choosing which one is sort of inorganic carbon and which is organic carbon. Well, that's organic carbon on the Earth, right? You've trained the AI on Earth organic. Is the same organic going to be on Mars? Well, we think so, maybe. That's our prejudice. We're jumping to a little bit of an answer, right? This is what, years ago, my mentors used to teach me, be careful about what you're assuming and check, right? That's the issue. Here's another example of AI. It's a very interesting problem to humans. Is there life on other planets? Right? So there's lots of other planets out there, and one of the ways we're going to tell most soonly is by looking at the atmosphere of these planets and seeing if we see chemicals that look like the chemical process of life. And so how do you do that? Well, you have actually a pretty big sample of planets that have been discovered, thousands, and many of them we actually have measurements of how much, the ones that transit in front of their stars, how much methane, how much water in the atmosphere. So you can plot those up as a function of the intensity, and you compare how they intersect and how common they are, and there's a plus on there in black, which is what the AI model predicted this should be, right? Well, again, it's a question of what information did you put in, what information you don't, but you're still going to find life. I mean, there could be a very large number of planets out there that have life on it. If there's some that's kind of similar to the life we're used to, you're going to find evidence for that, and that will happen within the decade. We'll see what happens. So we're using AI, but we're putting in human prejudice. Here's another example. Okay, and this is from down the hall from where my office is in Berkeley, is the breakthrough search for artificial intelligence. And so this is a cool robot looking through. I always wanted one of those transparent iPads, but I haven't seen one. But they have a whole series of radio telescopes that are out looking, synthesizing the beams to all the nearby stars that are available in the sky, looking for signals. And they run a test to see what they can do using the AI to look at the data from an Australian telescope, radio telescope, which has been used to discover the first generations of fast radio bursts, which are very sharp spike signals and so on. And so humans found a fair number of them, around 40 or 50. The artificial intelligence came and increased the number by more than 50%, maybe up 70% on that scale. So they're now set up to be using this artificial intelligence to look for signals coming from these 50 nearest stars or 100 nearest stars to see if they're going to see some evidence of something. And here's another thing that's interesting. There's a robot on the space station. I don't know if you know this or you guys ever paid attention. Looks kind of like an astronaut with really long arms, and you can put tools in the, you can snap on tools and stuff. And this robot does work. You tell it what to do, it uses learning. It goes and does the task, and it goes out and does it. It can go outside, it can go inside, it can do this kind of thing. They don't let it outside much because they haven't figured out how to make sure it can come back, right, or it will come back. But it's on board, and it's doing stuff. It's sort of like, if it cost $1 million a day to have an astronaut up there, can they do $100,000 worth of work before breakfast? How about this one? He can work all night, right? Okay, so here's another example. So there is a telescope, I think it was in Mauna Kea, the Subaru telescope, which is run by Japanese, but it's a big collaboration. And they have now got over 500,000 galaxies, and they have used the software to try and classify all those galaxies. And what they did when they ran through those 500,000 galaxies, they found that about 80,000 of them were clearly spiral galaxies. Now, that means there's 400,000 and something that aren't necessarily spiral. Some of them are spiral because you see them on edges. But this is a very quick way of classifying them. Doing this by hand is really difficult, right? So that's why you do AI, and the AI has to learn, and you give it a learning set, and it learns, and then it finds them, and then you look at it and see how well it did, and then you go back and refine it. But the Dark Energy Survey, which is a big international collaboration, they have very many millions of galaxies, not just 500,000, many millions of galaxies. So this is a problem. How do you do that by hand? In the early days, they had a project that was called Galaxy Zoo, and you got citizen scientists to volunteer to classify galaxies. And that was actually pretty successful because some of them stuck with it, and they actually learned, like the way the AI learns. The citizen scientists learned how to make the classifications do that. And it's not successful, and that gave them a catalog, which is over 1 million galaxies with classifications. And that was the learning catalog for the AI that now runs on the tens of millions of galaxies that exist, right? And it's pretty good, but I mean, you've got to look. Galaxies they're not like electrons or bowling balls. I like atoms because every atom is exactly like every other atom, right? You can trust them, they interfere, and they can do stuff. But the fact is, this is a big problem. You got 50 million galaxies, what are you going to do with them? How are you going to classify them? And there was a learning experience early on in Galaxy Zoo. They asked people to classify galaxies if they're rotating left or right. Well, it turns out humans have prejudice, and more galaxies are rotating one way than the other, according to the citizen scientists. But that would be very strange, right? That means angular momentum is spread across the universe in a funny way. And when you go back and study it and reclassify it, well, the humans have a bias. They tend to see things rotating right-handed, right? Except for the left-handed people. So we have two types of current AI, right, that are shaping our experiences. And I picked these out because they show you what goes on science too. There's algorithmic AI, which runs the recommendations you see on your social platforms, including when I log on to Amazon, they give me a list of things I might want to be buying and so forth. And there's a new world of generative AI. That picture at the beginning of my talk was an example. ChatGPT is another example. They're having a major impact because they're creating a lot of new stuff, right? And it makes creative people very scared, but it also means there's a whole lot of bad stuff coming out on the web because people are using that creative GI to put garbage out on the web. There are hidden factors that bias the AI. Mostly it's us. We've met the enemy and it's us. That's the real issue. You know, we have a naive view that we're going to run the AI and it's going to give us an unbiased set of stuff. But that's not what happens in your really life. In your really life, they try and get you to click on stuff. They want to get your attention. They want you to keep following down the thing so you're 10, 12 clicks deep or worse or more, you know, hours into it. That's the experience that most people in the world are having. Right? And those guys are really good. They really engage people and they only care about engagement and they're really skilled at it. Right? And science has similar biases about AI. That's my concern. So the robots are here. Okay, so here's an example about how AI works that was kind of a good example, and that is the Dutch people were interested in how they could solve arson cases. And typically, arsonists take gasoline and they spread it as an accelerant and they set it on fire and they disappear. And you want to reconstruct from the residue what was the original gas sample so you can try and figure it out, because gasoline, like dynamite, often has chemicals in it so they can trace where it comes from. And so here you have some thermodynamic equation about the rate transfer. You have what the original thing looks like. This is a 4-level net, and then what the end products are like. And then you want to run the neural net backwards in a certain sense, figure out from what residue you have what the original one was, and you want to get it within 5% or whatever it is. So that's their goal, and that's what they claim they're doing. And here, it's interesting because they will actually put some physics or chemistry into the AI, whereas a lot of AIs don't have anything in it, right? It's just fitting. So let me say how are most people training their neural nets, right? This is a 5-level neural net, which is the standard tool that Google makes available to everybody. You have an input layer, some hidden layers, and an output layer. And what you're doing is basically summing linear equations. Linear inputs in and linear outputs out. There are the sums of so forth. And it's going down the situation. And you then adjust all the parameters, which there's a lot of parameters because each one of them has got 5, you know, in this case, each one's got 5 inputs and 5 outputs. So there's a bunch of coefficients for each one. And you've got to then optimize the coefficients. And so this is a problem. And as our first speaker was telling us, it's many-dimensional. Now in the CMB, at the end for Planck, we were solving 10 million by 2 million matrix, right? And we were doing it by iteration. And everybody else before that just wanted the principal components, but we wanted all of them because we wanted the full map. So we do Markov chain Monte Carlo. There are ways to do. The award was given to people for finding even more optimum ways to come down and find the bottom. When you look at this kind of stuff, this is based on a neural net. There's 3 kind of neurons. The first one we're talking about is there's the nucleus with the dendrites bringing signals in and the axon sending signals out. And you can model it by the neuron and the linear sum plus an offset out. That's the simple kind of thing. When you get to the stuff that it's recurrent, so you can do languages and so forth, there is a recurrent, you know, repetition or something, or imaging. Those are the kind of things. And that's what neural nets are all modeled on, just these kinds of things. But again, the linearity depends upon how many recursions you have and how much other things are going on. You're basically linear or quadratic, and that's how good the approximation is. So here's a plot of some examples of neural nets that I just picked out to show you the kind of stuff. But ChatGPT-4 has 1.7 trillion parameters approximately. It could be, depending on which one it was, it could be a little less than 1 trillion up to 100 trillion, depending on how weird a model you wanted to take of what's happening. Why do I worry about this? Well, this is something that I worried about a little bit, but now I worry about a lot. There's a growing tide of paper retractions, okay? And that's done because of different things. It has to do with the fact some of us are old enough to have had mentors from the previous generations that really stressed how you had to take a human out of the science and check be confident you could do the stuff and and do the cross-checks and the double cross-checks and the independent mind and have other people check it so that you have, that's why they're double-blind experiments in medicine. Well, the problem is, starting a decade ago, there was a tenfold increase in the number of retracted papers, right? That is, in those days, people were upset because it was 1 in 10,000, right? Nowadays, we have floods of retractions. It's not just a retraction, we have floods of retractions. That is, 100 papers, 200 papers at once being retracted from the journals or taken back out of the journals, right? And I gave you this example of this Joachim Bolt who fabricated the data. He had to retract 70 papers, and that's what you do when you're honest. If you see the paper's not right, you say it's not right. Now, about 10% of papers are retracted within 3 months of the time they're published. Some before they're published, some after they're published, but they're retracted. I was hoping that Adam Rees would be here because he and I had a discussion. I was very upset because I have a graduate student and a postdoc who are working on JWST data, and in fact, you saw some of that data. It was released to the whole world, not just to the team that was doing it. Usually when you have a new project like that, the team that's doing it has some limited time where they have the control of the data, and they get to do the tests and put out stuff that's quality, so other stuff's measured against. At JWST, they just dumped the data. As soon as it was taken, the data is just dumped and anybody can have access to it. And I said, we're trying to train these guys to do their science right. How can we compete with people who aren't doing the science at all, or just writing stuff, or who are professionals and cranking the stuff out really fast? How do we do that? And, how can we do it? And so Adam Rees said, we talked about this, and I was one of the people who came down on this side of we don't want to show any favoritism. We want to let the whole public have access right away. And I said, okay, I can understand that's a noble thing, but it's a bad thing. My prediction is, based on what I've seen so far, 30% of the stuff published about JWST in its first year is never going to be heard from again. It's either being retracted or just never even got published. It never even got in a preprint form. It only appeared in the newspapers and in magazines or online magazines. So this was also, I put this in for Adam, but he was on Zoom, but he wasn't here, so I could argue with him, give him a hard time. But here's a plot of the speed of light measurements from 1880 to 1980, to 100 years. Now, did the speed of light change during that time, or did the error bars get misestimated? What do you think? Well, could be either one, right? Could have, right? And here's the Hubble. This is H0. This is what I put it in for Adam. But you can see H0 change. What he didn't show you is down at the end, it splits into 2 pieces. And now, one of my best students went to work with him, and there's a tip of the red giant branch which comes right between the 2 pieces. So, and all the error bars don't match. So is it because there's some new physics, or is it because we're underestimating our systematic error? Well, I got my prejudice, but we're going to know in a few years, right? We'll see. Here's the thing that I was taught when I was just a grad student and higher. There were 4 requirements to be an author. You had to make substantial contribution to the work. You had to be involved in drafting and reviewing. You had to have a final approval. That is, you could take your name off or say you can't go in. And you had to be accountable for all aspects of the work. That you're putting your name on it meant you thought the whole thing was right. How are you going to do that? Being a member of a collaboration isn't enough to get you to be an author. You've got to fill this this is how I was taught as a young kid, okay? So how is this going to be possible with advanced AI? Okay. Here's the AI all writing papers, analyzing data and writing papers. They're taking the data, they're processing and analyzing observations, they're making the approximations. These are all approximations. These are not fundamental exact theories or mathematical, these are all approximation results. And they're writing the papers, right? Because ChatGPT is capable of writing a better paper than the average person. How are you going to determine who meets the criteria for authorship? So AI presents real opportunities, and it presents us from pitfalls. That is, AI is going to remain opaque and unreliable and likely to fail in a lot of situations. It comes down to the quality of the people and the quality of the training set and the training. That's absolutely critical. And so reputation is going to be more important rather than less important in the future. We give examples where computer vision is doing great, but it's an approximation, and we all know it's an approximation, but we're happy with computer vision because it lets cars drive around and lots of other things happen, right? Including the Mars rovers, right? So remember, all the models are wrong. There's no AI model that's correct. It might be close. That was your argument, it can get close. But they're wrong, and some of them are dangerously wrong. Some of them are actually usefully wrong, right? So we're going to make major milestones and discoveries, but we're going to screw up.